All right. The only major announcement I know about, well, there's a couple. One, this is the end of, this week ends the first mini-term, which means sometime over the weekend, that is midterm. So next week starts second mini-term, okay? And on Wednesday of next week, 1 week from today, I'm required to submit a report on student progress. It's a student progress report, midterm student progress report. Well, let me just take a look here. Got to find where I can't see. Every one of you are doing fine. So I will not turn in anything for this class. All they're looking for are D's and F's at midterm. All of you have A's, B's, or C's. In fact, it looks like maybe all A's and B's so far. So way too easy, of course, right? So we will. There won't be anything to report for this class. So I just wanted to check and make sure everybody had turned everything in. They have, and all of you are scoring passing scores. So that's great. I didn't know if any of you are interested, but there is a volleyball game tonight at 6. You can't go to it because we got class, but right after class you might be able to get over there just across in the Arthur Chorus Fine Arts Building. We have an excellent team and they're quite good. And if you happen to be up in Huntsville Friday or Saturday, they're playing in a tournament up there, so at Wallace State Huntsville. Okay. So anyway, there's that. There probably are some others. I can't think of what they are right now. Okay. Any questions on anything we have covered so far? Okay, where we left off last time is on Chapter 12, Matter, and we're in 12.5, Density, and this is probably one of the biggest sections in here. We did Example 1 last time, and we're ready to do Example 2 on page 331. And I don't think that this, I have enough room to write on that slide. Let me just see what my next, oh, this is the last slide. Okay. Nope, won't be doing, well, I may pull this up again for reference, but let's go back to here and go from current slide. All right. Example 2, page 331, if there are no questions or anything else. Okay. Find the mass density. So what we're looking for, their symbology for this, let me get my pen set up, is D sub M. Now other books, other texts may use different symbols for it, but that's what we're looking for. That's the unknown. Find that. Of a ball bearing with a mass of 22.0 grams and the radius of 0.875 centimeters. All right. And if I can find my pen, there it is, and find my grade book, there it is. I'll mark Trish here. There she is. Okay, good deal. Now, we're doing example 2 on page 331. All right. Do y'all know of any formula that relate mass densities to mass and radii? No. What is mass density? Mass per unit. Mass per unit. Top of the page. Basic equation. Top of page 331. Oh wait, that's weight density. In this very example, right at the middle of the page, mass density is, see it? Y'all got books? Page 331. Almost the center of the page. No, it's not velocity. Capital V is? Little v is velocity, capital V is? Is it loud? No, that's not the same one. Volume. Oh, not that volume. Okay, so what we're looking for is mass per unit volume. Well, is there any way to get a volume out of a radius? Now, this is a ball bearing. Y'all all know what ball bearings look like. Hint, balls, okay? Spheres, okay? Is there any way to get a volume of a sphere from a radius? And the answer is yes. Go to the back inside cover of your text. And that back inside page says formulas from geometry. The top part of the page are plane figures. Those are things in a plane, rectangle, square, blah, 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 blah. The bottom part says geometric solids. We're talking about a solid. A ball is a sphere. Sphere is a ball. And that's the very last one. And what's the formula for volume? Related to radius. You see it? Equal. A little bit louder. 4 over 3 pi r cubed, right? 4/3 pi r cubed. So that's our first step, is to find the volume is equal to 4/3 pi times the radius cubed. Okay? But I think we've got another problem, don't we? Well, let's look. Yeah. They want the mass density in the standard SI units, which would be what? What's the SI unit for mass? SI unit for mass. Say again? You may have said it right. I can't hear well. Mass. It's a unit for mass. Hint, I just wrote down 22.0 grams. Is that the SI unit for mass? What is the SI unit? Has a prefix before grams. Kilograms. Okay? So what we need to do is get the mass in terms of kilograms. So first, what unit do we put where? One goes on top of the first line or on the bottom? What unit goes where? Between grams and kilograms. One unit on top, one on bottom. Which goes where? It's your conversion factors. We've done it just about every class, folks. Second? Between grams and kilograms. One unit goes on top, one on bottom. Which one goes where? $50-50 chance. Make a guess. Where? On what? Top? No, on top. Kilograms on top, grams on the bottom. You see, now you can cancel out grams, and that leaves kilograms exactly where you want them, right? Now you match the number with the units. How many kilograms in a gram, or how many grams in a kilogram? 1,000 grams is 1 kilogram. Kilo means 1,000. 1,000 grams, 1 kilogram. Okay? So that means you're dividing by 1,000, meaning you move your decimal place 3 places to the left. So this is 0.022 kilograms. Okay? Now the book doesn't do it this way. They come up with this conversion that you have to go and look up in a table and stuff. You can figure these out by yourself. You get the same answer. You don't have to go looking all over the book and make sure you got it right. Okay. But we've got another problem, don't we, Houston? Okay? We've got our radius in centimeters and not meters. Now, this is going to be really messy, but it's doable. we need to change that centimeters to what's the SI unit for length? I just said it. I didn't mean to. Not centimeters, but meters. So which unit goes on top and which on bottom? Centimeters or meter? Which one? If meters were on the bottom and centimeters on top, you have centimeters squared per meter. You want to be able to cancel out the centimeters, so you put centimeters on the bottom, meters on top, then that leaves it right where you need to go. And how many meters in a centimeter, or how many centimeters in a meter? 100 centimeters in 1 meter. Think cents. 100 cents in a dollar, okay? 100 centimeters in a meter. That means you move your decimal 2 more places to the left, okay? Wow. This is 0.00875 meters. Okay. You need all those decimals there. And we also need one more zero here because you have to have 3 significant digits after that. Okay. So now we're ready to plug in our volume formula. That's 4/3 times pi times 0.00875 meters cubed. Now, what does it mean to cube something? So again? Okay, squaring is multiply itself by itself one times the other. Cubing, it would be multiplying 3 times. So you have an operator on most calculators that will do cubing, but if you don't have that, you can do 4 divided by 3 times pi. Now, do you have a pi key on your calculator? If you don't, you can use 3.1416, but most calculators do have a pi key. So it's 4 divided by 3 times pi times 0.00875 and then cube it. If you don't have a cube key, then do 0.00875 times 0.00875 times 0.00875. 0.00, okay. Be sure you do it 3 times and then hit equal and see what you get. It's going to be a tiny number. Very small number. What you get?
A really, really big number. I did it wrong.
No, it's not a big number. It's a very small number. So it's 4 divided by 3 times pi times, now 0.00875 cubed. If you have a cube key, if you don't, multiply 0.00875 by itself 3 times. 0.00, keep going. How many? 5 zeros. Okay. And what? 2806. That would be cubic meters. And I haven't worked it, but it seems like a reasonable number. Okay? All right. Now that we've got the volume and the mass in the proper units, we can enter the density formula. The mass density is the mass, which is 0.0220 kilograms, divided by the volume, which is 0.0002806 meter cubed. See what you get. A pretty reasonably sized number. I was going to say, I'm just going to give a ballpark guess here. I'm going to move this 6 places that way and move this 1, 2, 3, 4, 5, 6 places that way. And 2, 1, 2, 3, 4, 5, 6. Three will go and, yeah. Something around 7,000 or so. Point 0.0220. Don't worry about the rest of the stuff I put there. Divided by 0.00000, 5 zeros, 2806. Anyone got a number? 7,320. Is that what you said?
840.
7340.
840.
7840. Okay. In the book, they got 830. I think we're probably a bit more precise because they did a weird way of rounding theirs. So that would be kilograms per cubic meter. And that's a very reasonable units for density. Now let's see what it is. The density of a ball bearing, that density. If you go back to the table, that's 7840. Let's go back to the table. Anyone need this up any longer? Everybody got it? Okay. Then let me go back to the table. Have I said that enough times now? And 7,840 is what we got. That's really hard to read. Let's see if I can. 7,840. That looks like it may be an iron ball bearing. Okay? Because iron ball bearings, or iron has a density of about 7,800. So it's probably not pure iron, probably has some other things in it to keep it from rusting. So it could be galvanized iron or something like that, but that's a good guess of what it would be. Iron-based anyway. Any questions on that? Okay. Then let me get out of that and go back to my other and go from current slide there. I've got to get my pen back. Okay. Example 3, the bottom of the page. Find the weight density. This is D sub W. Question? Oh, okay. D sub W of a gallon of water. Okay. So what we have here is what they call a capacity. Okay. 1 gallon of water. Now, that's all they say, a gallon. Okay. 1 gallon of water weighing 8.34 pounds. So that's obviously a weight equal 8.34 pounds. All right. A gallon of water. That's a capacity. Now, give me the formula for weight density. It's the weight per unit volume. Just like mass density is mass per unit volume, weight density is weight per unit volume. We got the weight, but we don't have the volume. We have the capacity. So here's where we go. Now, it also gives it in the book, but to tell you where to go to find it if you don't have that handy, in the back of your book, Appendix C, okay, there's a Table 1 there, and this is on page 686, U.S. weights and measure. We don't need that now, I don't think. Conversion table for length, that's not going to help us. Conversion table for area, that's not going to help us. Conversion table for volume, Table 4 on page 687. That looks like it might work. And you see on that table, it's on the very first maybe quarter of the page, the very next to the last line there, 1 U.S. fluid gallon equals 4 U.S. fluid quarts. We knew that. 8 U.S. pints. We knew that. 128 U.S. fluid ounces. 231 cubic inches, or 0.134 cubic feet. That's what we need. Okay? That's going to be our conversion. Get something in place here so I don't lose my place. We have a gallon, which is the capacity, times blank blank, yuck, that's not very pretty, equal blank cubic feet, because your volume is in cubic feet. And what unit do we put where? Pounds goes where? No, there's no pounds here. Gallons and cubic feet. One goes on top, one goes on bottom. Which goes where? What's that? It's the gallons goes on the bottom and cubic feet on the top. Then that's the only other choice, only other place it could go. Now you look at the table we just looked up. It tells you 1 U.S. gallon, so you put a 1 down here, is equal to 0.134 cubic feet. 0.134 cubic feet. Okay, now we've got the volume. 1 gallon times that is 0.134 cubic feet. 1 times that divided by 1 is that. Okay, that's how many cubic feet are in 1 gallon. We didn't even need the measures here. I just did it so you get used to doing your conversions. Okay, so that answers that question for us. Now we've got weight, 8.34 pounds, divided by 0.134 cubic feet. And you punch that on your calculator and see what you get. And by the way, I said weight. The book does F sub W. So I'll do F sub W too. The force due to weight, which is the weight. Punch that in and see what you get. A little louder.
62.23.
So that's what? Point what?
0.23.
23?
Yeah.
That would be cubic feet. Okay, we only have, well, we don't have many digits at all. The most we see there is 3 significant digits, so I know we can't use 4, so let's round that to 62.2 cubic feet. Okay? And in your book, you get 62.4. Now, how they got that is not at all certain. Okay? Oh, I see what they did. Oh, silly way to do the problem. They first converted gallons to cubic inches, then converted cubic inches to cubic feet, and that's not really the best way to do it. Go straight from gallons to cubic feet. And you came out a little bit short of what they gave in the table, but 62.2, 62.4, you're not going to lose any points on that. Okay? Make sense? All right. Example 4. Can I go on and erase this? Now, come here so you can see it. I don't know what 50, 00, that doesn't stand for anything. So I worked out the problem. It needs another 0 there. So it's 50,000 pounds, and this one's 60,000 pounds.
Okay.
Okay, the rest of it I think is right.
Okay. Thank you.
And by the way, for all of you don't leave without a test tonight, because I think we'll get far enough along to finish the chapter tonight and hopefully get started in the next one. All right, top of page 332, example 4. Any questions on this before I erase it? Okay. Example 4. Find the weight density, D sub W, we've had that before, of a can of oil, 1 quart. So again, they give us a capacity of they just say 1 quart, okay? 1 quart weighing 1.90 pounds. So the weight, which they call F sub W, is 1.90 pounds. Okay? Now, what seems to be something we need to do in this one? What's the formula for density? Weight density? Just had it. It's the weight, which is force due to weight, divided by volume, what it's always been. Okay? What's that?
I keep wanting to say velocity.
Yeah, well, the V was velocity a few chapters ago, but that was little v. Capital V is volume. Okay. Now, we've got our weight. They gave it to us. But they didn't give us our volume. They gave us capacity. So again, we go right where we went before. And this time I need to move my pages here. And that was the back of the book, same page, 687. This time we're looking for the conversion between quarts and cubic feet, because our density will be a volume in cubic feet. Well, unfortunately, they don't have that specific conversion, okay? But they do have on that same line we were doing before, you see that one that says 1 U.S. fluid gallon equal 4 U.S. fluid quarts equal 8 U.S. pints equal 128 U.S. fluid ounces equal 231 cubic inches, which is 0.134 cubic feet. That's all we need, okay? Because what we can do is do dot, blank, blank, equal blank. And what are we going for? Density is measured in pounds per cubic foot. So we need cubic feet. So you tell me what unit goes where? Anybody?
Cubic. You said cubic feet.
Goes where?
The bottom.
Not on the bottom. Top, because that's where it is here. It's on top. Cubic feet. And then quart, the other one has to go on the bottom. But you look at the table and there's not a direct conversion, but if you look at that line we looked at before, there it says 4 quarts. Do you see that? 4 U.S. fluid quarts equal 0.134 cubic feet. You see that in the table? It's not 1, it's 4 of them. That'll still work. So what do? Divide 0.134 by 4. And that gives you 0.0335. Is that right?
Yeah.
I'm doing it in my head. Okay. 0.0335 cubic feet. So then your weight density will be the weight, which is 1.90 pounds, divided by your volume, which we just determined to be and this, by the way, is volume, 0.0335 cubic feet. Okay. Looks like to me that's going to be something on the order close to 60. Let's see. Yeah, close to 60. 50 something, 60 something.
So
I can't do that in my head.
I'm still writing.
Say again?
I was still writing. It's 56.71.
56.71?
Yes, sir. But in that case, it would be rounded up to 57.0.
No, wait, okay. That's pounds per cubic feet,
Yes, sir.
okay? But they only have one number given to us. That's 3 significant digits. This conversion factor was 3 significant digits, so let's round it to 3. So count. 1, 2, 3. Look to the right, that's a 1. So let's just throw away the 1. So 56.7 pounds per cubic feet, per cubic foot. Okay, let's go back and see how the book did. They had 56.9 because they used different conversions, and actually I think they introduced more errors by introducing more conversions. We did one conversion basically and it worked. So either one of those are close enough. Now what you might also do is want to go back to your table. Remember 56.7 or 9. Let's go back to our table we had before. And let's look up oil. 54.2. It's a little bit denser oil than what they had here. Okay? That looks in the right ballpark, right? Good deal. Let's go on to example 5. Anyone need, well, I've already lost the screen. Need this any longer? So let's get out of that and back to this one. Okay. Example 5. A quantity of gasoline weighs 5.50 pounds. So what we know here is, let me get my pen set up, the weight. They call that in this book F sub W is equal to 5.50 pounds. Okay? With a weight density, so that's D sub W, and that's equal to 42.0 pounds per cubic feet. 42.0 pounds per cubic feet, cubic foot. All right. You get is it Tierra? Okay. Got a real good memory. It's just short. Okay. All right. We're on in chapter 12, matter, and we're on the bottom of page 332, example 5. This is in section 12.5, density. Okay? So, we were just writing down what they gave us. We got a quantity of gasoline with a weight of 5.50 pounds. That's your forced due to weight, or weight. The weight density, D sub W, is 42.0 pounds per cubic foot. Find the volume. So what we're looking for is volume. Anyone want to suggest to me how I go about finding that? Same formula? Okay. What formula would that be then? dW is equal to F sub W, or W, I like either one of them, divided by volume. Okay? Now, you can either plug in the numbers and then solve for volume, or you can solve for volume and then plug in the numbers. Which one would you rather do? Chug and plug would be solving for volume first and then plug in the numbers. You want to do that? Okay. So solve for volume, multiply both sides of the equation, because I don't like volume in the denominator. I don't like the denominator, so let's get it out of there. Multiply both sides by volume, that gets rid of V there, and then we want to divide by the density. Okay? And that gets rid of density here. So you get volume is equal to the force due to weight, which is weight, divided by the weight density, which is d sub w. Now, the other way to do that, if you remembered your formula, that dW is equal to weight per unit volume, do your triangles or your circle over here. I like triangles, okay? Do the dividing line and the multiplication line. You know the formula here. The F sub W is on top, the dW is down here, and the V is down here, okay? Cover up the V, and you get weight density, force due to weight over weight density. Yep, that's exactly right. So, our weight is 5.50 pounds divided by 42.0 pounds per cubic foot. Not a bad idea to hang on to your units. Those are your friends. So you don't want to mistreat them. You want to keep up with them. Okay? So you do that. By the way, the pounds are going to cancel out. And 1 over cubic feet is going to be cubic feet. So all we need is the number, 5.5 divided by 42. It's going to be 0.1 something, right? Yeah, that sounds about right. I don't know. Tell me, I may have it wrong.
I was trying to see what the bottom number was.
It's 42.0, just 42. 5.5 divided by 42.
0.1309.
9. Okay. We've got 3 digits here, 3 digits there, so let's count 1, 2, 3 digits. Look to the right, that's a 9. We increase that 0 to a 1. 0.131 cubic feet. Okay. Let's see what they got. Oh, look at that. They got it on the nose. 0.131 cubic feet. Make sense? Any questions? Anyone need it up here a little longer? You are, okay. All right, good deal. Any others? All right, let me go and erase this, and we're going to do the next problem. The density of an irregular solid, like a rock, cannot be found directly because of difficulty in finding the volume. However, we could find the amount of water that the solid displaces, which is the same as the volume of the irregular solid. So in this figure, the volume of water in the small beaker equals the volume of the rock. Okay, so what you do, you have a beaker, they call this a, goodness, I can't think of the name of it. It's a beaker with a spigot coming out of it, basically. And what you do, you fill it right to the spigot. Okay? Usually you let a little water come out and catch it in the second beaker and then throw that water away. Okay? Now you take your rock, now make sure your rock is smaller than the volume that you have in the beaker, and you lower the rock very carefully into the beaker, and it displaces water. The water comes out the spout, you catch it in the other beaker, then you take that and measure what volume of water you got. Hey, pretty good way to measure an irregularly shaped object like a rock. Actually, I teach a physical science course, and we did this very experiment. We were doing the density of igneous rocks, we did granite, and we did basalt, and then an unknown rock, and we measured the density of all three. Okay, and that's what we did. We lowered it into a container of water and caught the water that came out. Now, a rock of mass, this is example 6, a rock of mass 10.8 kilograms. So there's the mass of the rock is 10.8 kilograms. Standard unit, perfectly fine. Okay? We're happy with that. Displaces 3,200 cubic centimeters of water. So that's a volume. 3,200. First zero has a bar over it, meaning it is significant. The last zero is not significant, and that's cubic centimeters. Okay? What is the mass density of the rock? Well, guess what? We don't want it in cubic centimeters. What do we want it in? Blank, 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 blank. What unit do we want the volume in? Not cubic centimeters, but cubic meters. So we want it in cubic meters because that's what we use, the SI unit. All right? You tell me which unit will go on top, which in the bottom. Meters on top and centimeters on the bottom. Now, before we put the cubes in there, let's put the conversion factor. How many meters in a centimeter or how many centimeters in a meter? 100 centimeters, like 100 cents in $1 or 1 meter. Okay, 100 centimeters in a meter. Now, let's cube everything. We need to cube the meters, cube the centimeters, cube the 1, but we also have to cube the 100. Whoa. 1 cubed is just 1. Okay? 100 cubed, though, is 100 times 100 times 100. So for every one you do, you add 2 more digits, 2 more zeros. So it's 1, 0, 0, 0, 0, 0, 0 centimeters cubed. So that's 1 million cubic centimeters. Okay? So what we do now is move this decimal 6 places to the left, because that's how many zeros you got there. There's 4 to here. 1, 2, 3, 4, 5, 6. So that's going to be 0.00320 cubic meters. Okay? Now, I think we're ready for our formula. It says, what is the mass density of the rock? That's what we're looking for. The mass density, and what is the mass density? What's its formula? Mass per unit volume. And we had our mass of 10.8 kilograms divided by a volume of 0.00320 cubic meters. Pull out your handy-dandy calculators and see what you get. I'm just going to do some scribbling here so I get an idea what you got. Move that 3 places here, 3 places there, and that would be, looks like about 3,000 and something. 3375. That sounds reasonable. 3375, and that would be kilograms per cubic meter. Except we only have 3 significant digits here, 3 significant digits there. So let's count 1, 2, 3 digits. Look to the right. That's a 5. That's going to bump up the 7 to an 8. So that'd be 3380 kilograms per cubic meter. Okay? Let's see how the book did. Oh, look at that. 3380 kilograms per cubic meter. Now, they do their conversions differently. This, to me, is the easiest way to do the conversions. Otherwise, you have to remember what unit goes where. It works out the same, but to me, this is just a little easier. Anyone need this a little longer? Any questions on it? Everybody got it? Okay. There's a somewhat similar at the bottom. Let me clear this, if it's all right to erase. a rock displaces 3 gallons. That's a capacity. The capacity is 3.00 gallons. That is a very special rock to displace exactly 3 gallons of water to the nearest hundredth of a gallon. That is incredible. And it has a weight density. This is the rock that does. So the D sub W is equal to 156 pounds per cubic foot. What is the weight? So we're looking for F sub W. All right. Now what's wrong with this picture? What is that weight density? What's its formula? The weight, F sub W, divided by the volume. We don't have a volume. We have a capacity. Okay? So what we're going to have to do is multiply this by blank blank to equal blank. And what volume unit do we want to have? This is SI, and this is not SI, this is U.S. customary. You can see it right here. It's either going to be pounds or cubic feet. Which one you reckon is a volume? Cubic feet. So we want this to be in cubic feet. So we go back to our handy-dandy table in the back, which we've used repeatedly today, and we have 3 gallons, 3 U.S. fluid gallons. That same table, table 4, page 687, the top table on that page, but it's next to the last line in that top table. 1 U.S. fluid gallon. Oh, I forgot to ask you. What units do we put where? Between gallons and cubic feet. One goes up, one goes down. Which goes where? Gallons goes where? Bottom, absolutely. Putting cubic feet on top. That way the gallons will cancel out and cubic feet's right where we want it. So if you go across that table and you see 1 U.S. gallon, I'll just write that down. 1 gallon and go down across that line. 4 quarts, 8 pints, 128 fluid ounces, 231 cubic inches, or 0.134 cubic feet. 0.134 cubic feet. Yes?
Did you say the table was on 689?
On page 687. There's another one on 689, but let's see what that's measuring. That's table for pressure. Yeah, we're not doing pressures here, we're doing volume. So that's the table 4 on page 687. And you see that next to the last line says 1 U.S. fluid gallon, 4 quarts, 8 pints, 128 cubic fluid ounces, 231 cubic inches, or 1.134 cubic feet. That's what we put up there because that's what we wanted to go to cubic feet. So you just multiply 3 by 0.134, and that gives us, that's be a 12, carry a 1, that'd be a 0, and that's a 4. 0.402 cubic feet. Right? Okay. So now we're looking for the weight. Okay. Our formula is dW is equal to FW divided by V. Do we want to first solve for FW so everything's where it belongs, or do you want to plug in first and then solve for FW and put it where it belongs? Up to you.
The first one.
Huh?
What'd you say the first?
The one that you want to solve for FW? Okay, we'll do that. So let me write it down here. This is equal to D sub W. Okay, first we don't want volume there, do we? So let's multiply both sides by volume, and guess what? That'll give us exactly what we want. That'll be the density, the weight density, times volume. Well, the weight density was given as 156 pounds per cubic foot. I'm going to multiply that by volume, 0.402 cubic feet. And boy, units are your friends here. Look at that. The cubic feet go out. That gives us an answer in pounds. That's a great unit for weight. So what does that give us? 0.4 times 156. Oh boy. Say again?
62.71.
62.71 pounds. Okay, except we only have 3 significant digits there, 3 significant digits there, 3 significant digits there. We have 4 here, so let's count over. 1, 2, 3, look to the right is a 1, so just drop the 1, 62.7 pounds. That's what we think the weight of that, what was it, a rock? I don't even remember anymore. Yeah. This place is 3 gallons of water. That's a pretty hefty rock to displace 3 gallons of water. And they got 62.6. We got 0.7. That's because they did really weird conversion. Okay. But it's still within 1 decimal place. Okay. Now, there is another concept here that we use sometimes in place of density. And that is the concept of specific gravity. And what specific gravity is, okay, what specific gravity is of a material is the ratio of the density of the material to the density of water. Okay, so it's the density of the material, that's not mass density, to the density of water. Okay, and that's not weight density. Okay, so my DWs are not the same as what their DMs and DWs. Okay, it's the material, let me spell it out. Material density divided by water density. Okay. Now, I'm going to give you a hint. If you're in SI units, okay, not quite SI units, metric units, and you get your density in grams per cubic centimeter, that's going to be exactly the same as specific gravity, except specific gravity has no units. Because density of water is, of material is in, say, kilograms per cubic meter, density of water in kilograms per cubic meter, those units cancel out. Specific gravity has no units. Okay? So, it says, note the specific gravity is a dimensionless quantity. So they wrote, there's close to the same thing I did. They call it SPGR, specific gravity. It's density of material over density of water. Okay? So let's do example 8. Can I erase this? Okay. The density of iron is 7830. So this is density of iron, Fe, is 7830 kilograms per cubic meter. Now, which density is that? Mass density or weight density? Say again? You may have said it right. Mass. This is mass density. So this is D sub M, okay, for iron. So I'll put iron here. Fe stands for iron. That seems strange, but it is. Okay? Find its specific gravity. Well, specific gravity, which they call SPGR, is equal to density of the material divided by the density of water. Okay? They look awfully close, but they are different. We got the density of material. That is 7830 kilograms per cubic meter. We need to divide that by the density of water. Well, you don't need to go to the back of the book for this. Just flip back flip back just a couple of pages, and there you see table 12.2, density of various substances, fine water, and the SI units. What is the density of water? 1 1,000 kilograms per cubic meter. Okay, so guess what that means? Move both decimals 3 places to the left, and you get specific gravity for iron to be 7.83, and the units go away. Specific gravity is always dimensionless. So it's specific gravity of iron, 7.83. Excuse me, no units after it. Okay? Now, if they had given a table of grams per cubic centimeter, that would have been exactly the unit. Now, this is a bit bizarre. In the table, they give iron as 7,800. That's either rounded to two digits rather than 3, or else this is an iron that is a little bit heavier. Maybe it has an alloy in it or something. Okay, so 7.83 is the answer. Ready for example 9? Yay or nay? Sorry, I've been having trouble breathing, so I get tired really fast because I'm not getting enough air. For some reason, I'm all clogged up. All right, density of oil is 54.2 pounds per cubic feet. So this is density of oil is 54.2 pounds per cubic feet. Okay. Oh, another thing, when you get a density, a specific gravity, and you have that number, if that number is greater than 1, like 7.83 was, that means that thing's going to sink like a rock, okay, like iron, okay? If it was less, that means it's going to float. So it depends on whether it's less than 1 or greater than 1, okay? So here we have oil, which is density of 54.2 pounds per cubic feet. It says find the specific gravity of oil. Okay, and what would that be? Density of oil divided by density of water. Now we just looked it up to see what it was. Density of oil they gave to us, 54.2 pounds per cubic foot. And we can look up in the table, or maybe you remember what the density of water is. In weight density. What is that? No. That's SI units. This is in U.S. customary. 62.4, and that's pounds per cubic feet. And that's the dead giveaway. The units have to be the same. If you were to put down kilograms per cubic meter, say, oh, wait a minute, wrong units, okay? So these units go out because specific gravity has no unit. So you punch in the numbers, see what you get. 54.2 divided by 62.4. Is that about 9 or 8? Anybody? Second? 0.8685, and no units with it because the units canceled out. Now we had 3 digits here, 3 digits there. We've got more than 3, so you count 1, 2, 3. Look to the right. It's a 5. That means you bump it up by 1, 0.869. Should be the specific gravity for that oil. Let's see what they got. 0.869. Good for them. Okay. Now, reiterating what we just said before, in general, specific gravity of water is 1 because it's a ratio of specific gravity of water to specific gravity of water. Density of water to density of water. That's going to be 1, okay? So any material that is denser than water is going to have a specific gravity greater than 1. And any material less dense than water, like oil, that's going to float. That's why when you have an oil spill, the oil will float on top of the water and make that film on top. Now that is really bad for fish and birds and things because that means you're blocking the oxygen from getting down into there. Fish can die, and birds or other things that land on that now get their feathers and everything else coated with oil, and they don't operate properly, okay? And so that's why you see them washing birds a lot, because the birds can't fly once they have been coated with oil. Now, that leads to a device that's called a hydrometer. That's a device that measures specific gravity directly. I don't know, have y'all ever used one? Have you ever seen one used? You may have seen it and not known what it is, okay? If you've ever gone to, say, the service station or something like that and say, do I need to do anything to my water in my radiator, okay? In other words, maybe add some antifreeze or something else. What they'll usually do is take a hydrometer, drop it into the radiator so they can see it, see where it lands, read the specific gravity on it to see if it's high enough or low enough. Because usually your antifreeze is going to lower the specific gravity of water, I think. Okay. So, no, it actually raises it, okay? And the other place you use it is in your battery. Okay, I said the antifreeze, specific gravity antifreeze also raises it slightly, okay? So for your battery, you want that battery to read the liquid in there to be about 1.30. If it's an old battery, almost discharged, it will probably only read 1.15. This is their table in the book. If you are worrying about antifreeze and stuff, if the coldest you're going to get is minus 1 degree Celsius, 1.24 degrees Celsius, you'll need specific gravity of at least 1, okay? That means just pure water will do. That's just barely 2 degrees Fahrenheit below freezing. But if you're down to 3 degrees below freezing Celsius, which would be closer to, by the way, let me back up. 2 degrees Fahrenheit below freezing would be 30 degrees, Fahrenheit. So usually at 30, plain water is good enough. But if you're 3 degrees below Celsius, that's going to equate to about 6 degrees below freezing. That would be Fahrenheit degrees. So 6 from 32 is about, get down around 26 degrees Fahrenheit. Yeah, you're going to need some more antifreeze. When you get down to minus 6.89, which is almost 7 degrees below zero in Celsius, that'll be about 13 degrees Fahrenheit. So 13 from 32 would be about 19 degrees Fahrenheit. Okay. When you get around there, you need a specific gravity of about 1.02. You can continue going down the table. We'll get down to, say, minus 19 degrees Fahrenheit, possibly. Are we going to get down to minus 20 degrees Celsius? That's equivalent to about 40 degrees below freezing Fahrenheit. Not quite, but close to it. That would be minus 8 degrees Fahrenheit. I've never seen that in Georgia or Alabama, so don't think you're going to need that much. But it wouldn't hurt, but you could have it. All right. Anyway, finishing that. Other specific gravities of common liquids at room temperature: benzene. I don't know what you use benzene for, but that's a little less dense than water, 0.9. Ethyl alcohol, quite a bit less than water, 0.79. Gasoline, even less, 0.68. Kerosene, 0.82. Mercury, 13.6. Mercury will sink like crazy. Okay. The trouble is mercury is also a liquid. Seawater is just a little bit denser than fresh water, so 1.025. Sulfuric acid sinks. That's what makes your battery a higher specific gravity. That's what you put in the battery, sulfuric acid. So that's what brings that specific gravity up. Turpentine is about like kerosene, a little bit denser than kerosene, but still less than its water. And water is exactly 1.00. That's the specific gravity. Problems at the end of the section, 12.5. You can do any of the odds 1 through 7, any of the odds 9 through 37. Okay? And you could break those down a little bit more. I'd say 9 through 23, and then do any of the odds 25 to 29, any of the odds 31 to either 31 or 33, and then either 35 or 37. A little bit of review, the glossary, the terminology, that's there. Formulas are there. Quite good to keep up with those formulas. Review questions, that's pretty much conceptual stuff, so you can look at those if you want. But then the review problems, these will be far closer to what you see in your test, and that would be any of the odds 1 through 19 would be good there. And those answers are in the back. That's why I give you the odds. So do that. Now, since we're at that point, let me stop here and give you the tests. All right. Now, this test does have 2 corrections on it. Oh, man, I've been sitting too long. I get stiff. All right. Both corrections are on question 3. And if you see how that originally looked, you'll see it doesn't even make sense the way that it wrote it the first time. And what's that? Oh, was that the first test? The second test I haven't given back yet. You ready to turn it in? I still have a couple people who haven't turned it in yet. So I can't give it back until everybody's turned it in. Oh, man, I'm stiff. Okay. Johan has submitted hers. And let's see, earlier. Okay, let me see. Nope, there's still 2 people haven't turned in the test, so I can't return them until the other 2 do. All right. So let's move on. Any questions about Chapter 12? Okay. Let's get out of here then and go to that's not what I wanted to do. Yeah. That's where I want to go. Chapter 16 is next. And starting with 16, we'll go 16, 17, 18, and 19. So we'll do 4 in a row there if we get to 19, but let's do what we can. Now, what are y'all planning to go into? What field? Say again? Ultrasound. And guess what the title of chapter 16 is? There it is. Let's go to current slide. Chapter 16, wave motion and sound. Okay, so we're going to start with waves, and then we'll move into sound. Okay, so let's start with that. Now, I'm going to be talking about 2 different concepts here for part of the time. Okay, they're related to each other, but they are different. One is the actual wave motion, and the other is the direction of energy transport. And what they say here, energy may be transferred by the motion of particles, okay? And that is called wave motion. And we're going to talk about at least two different kinds of waves, and they're a little bit different in how they act, okay? So, I think it's probably going to be better to go to the other slide first. So let's do that one first. Okay. As in most of these chapters, they start off with a bunch of definitions. So let's see what our definitions are. First one, let me get my pen set up. It's going to be a wave. Okay. A wave is a disturbance, okay, that moves through a medium A medium means some material like air, liquid, solid, whatever, through a medium or through space. Later in the chapter, we'll be talking about waves that go through space. Right now, we're going to start with mostly ones that go through air or a liquid. When you're doing your sonography, you'll mostly be looking at sound waves that go through tissue. Now, the tissue is usually liquid, but it can be somewhat solid. If it's bone, it's going to be very solid. Okay, so that's basically what you're looking at. Now, that disturbance may be a displacement of atoms away from their equilibrium or rest position, or in an elastic medium, or the change of pressure in a gas, or a liquid. So it could be a variety of things. Even in space where there are no particles, it's going to be change of an electromagnetic field. But we'll wait and get there later. Okay. Now, so wave is your disturbance. Another term is a pulse. Okay? Is a non-repeated disturbance that carries energy through the medium or through space. Non-repeated disturbance that carries energy through the medium. Our writing stinks. Or space. Okay. Okay. Now, that sounds almost like a wave. Okay? But the pulse is basically a thing that gives it the energy, that makes the disturbance happen, and then it's carried through. The wave is the actual disturbance of the material. All right. Now, two types of waves are mentioned here, and I'm going to split these up. And the first is called a transverse wave. Okay. And this is a wave, so it's a disturbance. Very disturbing chapter so far, isn't it? Okay. A disturbance through the medium in which the motion of the particles is perpendicular to the direction of the wave motion. I'm going to use that as a symbol for perpendicular direction of wave motion. Okay.
Perpendicular is across, right?
What's that again?
Perpendicular is across, right?
No, it's at right angle to. Here's my classic example of this. It takes me back to my childhood, okay, when we were doing something and had a hose laid out across the yard, okay. I was a weird kid, I guess, because I just loved to go and pick up that hose, yank it up as far as I could, and yank it down again. And what happened? It sort of down the yard, right? That's a transverse wave. The motion was up and down. The wave motion was that way.
Like this, right? Like
yeah, perpendicular to it. Yeah. So you do this, and then it goes down the yard. You've seen it, haven't you? Yeah. Okay, you're a weird kid too. No.
Yeah.
Okay. All right. Yeah. And it was just, yeah, I like seeing that happen. I didn't know I was making a transverse wave, but I was. That's what a transverse wave is. The disturbance up and down created wave motion that was perpendicular to that. The hose, made that little snake-like stuff going down the yard. You could do it this way too. Your motion is back and forth like this, and yet the wave moves perpendicular to that. That's a transverse wave. All right. Now, I'm going to come back to the next bold word, but I want to next do longitudinal wave. As opposed to transverse wave, in a longitudinal wave, the disturbance in the medium, okay, in which the motion of the particles is along the direction of wave travel. Not perpendicular to, but along the direction of wave travel. Have you experienced any of these waves today? Sure you have. Sound, sonography, is longitudinal waves. If you hold your hand in front of your mouth while you're talking, you'll feel little bursts of air, right? Say something. You feel a little burst of air? Those are called compressions and rarefactions. Those are waves. Those are longitudinal waves. That's hitting your hand like this, the air particles are, and similarly, the wave is going like that, okay? So the disturbance is in the same direction as the wave motion. That's a longitudinal wave. And sound waves are longitudinal waves, okay? Sound is an example. Let's see, Another, the one they love to give, a spring. Yeah, they were talking about a spring earlier. A spring is usually a longitudinal wave, okay? And they'll show a picture of this a little bit later. Okay. Now, let's back up and talk about a few characteristics of a wave. Okay. The first of these.
I'm sorry.
Okay. Got that one. Okay. All right. Good deal. And what's that?
You got anything else?
Yeah. You want to do another test now?
Well, I want to take it. I take it.
Huh?
Is there any way I can take it?
Take it with you?
Yes.
No, these weren't take home. That was the one you could have taken this one home with you if you had done another wave one here. That was a take home.
Okay, well, I'll do one more.
Huh? You got time to do it tonight?
Yes.
Okay. All right. Let me find my grade book. It's under here. Okay. So you did what, 3, and that
One,
was
two,
6.
Yeah, 3 and 6.
So here, I forgot to bring your completed test. There's test 4.
Okay. And then I'm actually, when would I be able to maybe meet with you to get the other ones?
Well, tomorrow I'm on the Bessemer campus from 9:45. I'm in office hours 9:45 until 11:30. But then the class meets tomorrow from 1:15 until probably around 4. Tomorrow's the final exam.
So 1:15 to...
Yeah, but that's on the Bessemer campus.
Okay.
1:15 till around 4. Normally we go to 5:45, but all they got to do tomorrow is I got to give them their papers back,
Okay.
and they're going to take their finals, so they'll be leaving early. But I'll still be around till at least 4.
Okay. What's your office? What's your
Okay.
office number? I mean, office, the room.
Room is my classroom is 255. It's A255,
Okay.
and the office is A265.
Okay.
Are you familiar at all with Bessemer campus?
No, I'm not. But if
Okay.
I know where I'm going, I'll probably get in there and figure it out.
Okay. You know how to get to Bessemer
Yes,
campus?
sir.
You
Yes,
do?
sir.
Okay.
Yes, sir.
That big building in the middle of everything is the A building.
Okay.
And probably the best bet, if you don't know your way around it, when you pull in, you know where what used to be Bessemer Caraway Hospital
Yes,
is
sir.
now UAB West?
Mm-hmm.
Okay, there's a light there.
Yes, sir.
Okay, turn toward the college, not
Okay,
toward the
I got it,
hospital.
yes, sir.
Okay, turn there, and then you'll get to a fork in the road, go around the right side, and go all the way around the building till you're parallel to the expressway back there.
Okay.
And you'll see a glass doors that say Student Services.
Okay.
Go in that door and just ask somebody there at the desk. There'll
Okay.
probably be someone at the desk.
Okay.
And where 255, my classroom, or 265, my office is, they're at opposite ends of a short hallway.
Okay.
And there's a half stairwell in between.
Okay.
But the 255's up at the top and 265's at the lower part, the other way.
I'm just trying to do this from tomorrow. Yeah, I come tomorrow.
Oh, tomorrow?
Yeah,
Okay.
'cause my brain about fried.
Okay.
Okay.
All righty.
I do it tomorrow.
Okay.
That's right.
You think you'll come in the afternoon then?
I'm gonna try to come in the morning.
Morning? Okay.
And catch some of them, and then if I can come back, then
Okay.
I'll come back too to get it all done.
Okay.
Take as much as I can.
All righty.
Thanks.
Uh-huh. Okay, I'm sorry about that, folks. Okay. All right. The next definition I was going to do is one called amplitude. Now, here's how we represent a longitudinal wave. Just like that hose snaking across the yard, it does like that, right? The motion of the particles is up and down, but the wave travel is one direction or the other. So this is what we call the equilibrium. I'm not drawing this too well. Equilibrium position. What amplitude is, I've already drawn where I was going to write it. Amplitude is the distance above or below the equilibrium position. Okay? Maximum displacement of the particle from the equilibrium or rest position. Maximum displacement of the particle from the equilibrium or rest position. Okay. This is an or there. I don't know why it came out so weird. Okay. Now, a little harder to talk about amplitude for a longitudinal wave. For a transverse wave, it's pretty obvious, okay? For a longitudinal wave, if you think about it, and I'm not saying anything, the air molecules are perfectly still. But when I talk, then some push this way, and then when I refract, they come back. So they go back and forth this way. That's their amplitude from the rest position, okay? But of course, they're moving in this direction, so it's a harder concept to hold. But in a transverse wave, pretty easy to recognize that way, okay? Now, the next concept here is wavelength. And by the way, the amplitude is a displacement. So that's going to be measured in a distance unit, like centimeters, millimeters, inches, whatever. Those are lengths. Wavelength is also a length measurement. So that's also measured in terms of a displacement, okay? The symbol for wavelength is lambda. That's a Greek letter corresponding to our letter L, length, lambda. That's the shorthand for, that's the minimum distance between particles that have the same displacement and moving in the same direction. Minimum, now this is a strange definition, distance between two particles moving in same direction, moving in the same direction. Okay, now that sounds a little bizarre, but I think when you see it, it'll make a little bit more sense. Okay, along the direction of wave travel, I left that part out. Here is your example of wavelength. Here's a point, they say at the peak or the crest. There's a point at the peak or the crest. That's the wavelength, the distance between here and here. That's your lambda. The wavelength is the distance between crests or troughs. Same wavelength. Or this point and that point. Now you might say, wait a minute, how about this one here? No, that's not a wavelength because this one's moving down, this one's moving down, this one's moving up. So you'd have to do this point to that point. And there again, that's one wavelength. So that's what they mean, 2 points, the closest distance between 2 points that are moving in the same direction. That's a wavelength. Okay. Now, the period of a wave, okay, is the time, not distance, the time required for a wave to pass, a single wave to pass a given point. It's, again, a single wave okay. Now, let's just say we've yanked the hose up in the air and down, okay? The length between here and here, that's the wavelength. But the time it took, I'm going to put delta t, the time it took for it to be at this crest until it reaches the next crest, that's the period. That's the time period that it took for the point to move from here up to here again, up to here again, or down here to down here again. The same point in the same direction. It's the time required a single wave to pass a given point. Okay? Now, one more word, frequency. Now, these other words you might use in sort of everyday English some. Frequency you probably use some, but I'm not sure you quite have a good feel for what that means. Okay? I'm going to give it to you one way. Let me go back to period. The time for a wave to make one cycle. From crest to trough to crest, that's the time for one cycle. What frequency is the number of cycles in a given time. So, period is time for one cycle. Frequency is cycles per a given time, for a unit of time. So it's the time, number of complete waves passing a given point per unit time. Okay, I've shortened it considerably. The guy who came up did a lot of work on frequency. His name was Heinrich, good German name, Hertz. Okay, have you ever heard of a hertz? That's what we use to measure frequency. Sometimes we have other units in front of it, like kilohertz, megahertz. You can even sometimes see gigahertz. You probably will see some larger, but these are frequencies. Kilo means thousands of hertz, mega means millions of hertz, and giga means billions of hertz. Okay, so those are sound is usually measured in hertz. Radio waves are measured in kilohertz if it's AM waves. Your FM waves are usually megahertz, and your super high frequency are measured in gigahertz. Radar and microwaves are in gigahertz. Okay, frequency FM radio megahertz. So they go on. All right, those are most of your definitions. Let's exit this one and see a little bit of your pictures. Okay. All right. Now this is what we were talking about before, and this is a representation of a transverse wave, but you could use it in a sense to talk about a longitudinal wave as well. But here's the typical definition. This line here is your equilibrium or rest position. Okay? Your crest is the very highest point from there. The trough is the lowest point. The measure here is your amplitude, or there is your amplitude, the maximum distance from the equilibrium line. Okay? Your direction of wave travel, they're saying here, so then this would be, an amplitude, by the way, is a distance measurement, how far above the equilibrium it goes. Your distance between crest to crest or trough to trough, the minimum distance between there is your wavelength. The time it took for it to travel from here, down here, and up here again, that's the period. And then 1 over the period, the reciprocal of the period, is the frequency. And I know in sonography, y'all are going to be dealing with frequencies a lot, so 1 over that is your period. Though I'm not sure you'll be needing that much, but perhaps, I don't know how what they focus on there. All right, here's a picture of your longitudinal wave, and they're using a spring here rather than air molecules, so that's easier to picture here. Okay, let's say you're holding a spring out here, okay? And then what you do, you're holding it so it's got some separation between the coils, and what you do is poke it and bring it back, okay? When you poke it, that's your condensation. That is your pressing them together. And then when you pull them back, that's what they call the rarefaction, separating, okay? And when you do that to the spring, you'll see that condensation go here and then ultimately here. And it could be, you'll see it bounce off here and then come back again, okay? And frankly, when y'all are doing sonography, that's what you're doing. You're watching for the reflection. And that tells you about what's been happening of the material you went through. So that's this is like your amplitude, okay? You might think of that, how much you compressed it. And you only had one here, so it doesn't really have a wavelength in this. But that would be how much you compressed would be like your amplitude, how much you deviated it from normal. So that's a picture of a longitudinal wave. Same thing that's happening with sound. Okay? Now, here's the one that I was pointing out that shows your wavelength. Okay? You can measure a wavelength from crest to crest, from trough to trough, or equilibrium position to the equilibrium position going in the same direction. Not this one. That's the equilibrium position too, but here the wave's going down, here it's going up. So you have to wait till it's going down again. That's why we usually don't use these. We use crest or troughs because there's only one of those per cycle. Okay, if you use a point here, you'll have one going, this is going down, that's going up, you have to wait till it's going down again. That would be a wavelength. That's a distance. If you're talking about the time, the period, how long it takes to move from here to there, that would be, the time part is your period. Hard to show that on here. Does that make sense? Oh, and by the way, this would be your amplitude, or that would be your amplitude. The maximum displacement from the equilibrium position. That's a displacement, so is wavelength. Measured in meters, centimeters, feet, inches, whatever. All right. Now, not quite ready for that one yet. Now, the one formula, I didn't write it down, but let's do it here, is period and frequency. And by the way, let me write this down too. Rather bizarre here, but true. I tried to get my pen. Okay, there we go. Period. Okay. Period. The symbol for period is capital T. Period is capital T. But think of it. It's a time measurement. So capital T is not a bad choice for that. Okay. Frequency, the symbol for that is just F. Okay. Now, if you were in an advanced physics course, sometimes they use something else for frequency, but we're not going to confuse the issue with that. Now, how are these related? Remember, period was the time for one cycle. The frequency is the number of cycles per unit time. So those are inverse relationships to each other. So you can say frequency is equal to 1 over period. Okay? And that's how we usually measure it. Remember, period is measured in seconds usually. Frequency is measured in hertz. And by the way, since they already had a unit in electricity named a Henry, and they used capital H for that. They decided not to use capital H for Hertz, but use HZ, the first and last letter of his name, Heinrich Hertz. So that's what we represent that was. So what a Hertz is frequency is measured in, and there's a couple. You can use a symbol HZ. An equivalent symbol would be S to the minus 1 or 1 over S if you're dealing in seconds, and that's what Hertz deal with, seconds. So all three of those are the same units. A Hertz, a per second, or a second to the minus 1. And that's because this is in seconds, this is in Hertz, so a Hertz is 1 over a second, or second to the minus 1. All right. Now, given that, we also talk about something called propagation velocity. Now, I don't know for sure in sonography if you'll be measuring or studying that or dealing with it, but I wouldn't be at all surprised if you wouldn't be, because that's the speed at which the wave is going, the sound waves are going through the material that you're trying to measure. Okay? So that's propagation velocity. Now that symbol is just like we used in way back in chapter 5. Velocity is V, and V, if you remember, velocity is distance per time, right? Okay? Distance measured in a distance unit, like wavelength per unit time. So this is your wavelength. Your propagation velocity is wavelength per unit time. Meters per second, centimeters per second, something like that. Okay? They use SI always. Okay. Now, because 1 over time is frequency, you can also say this is lambda F, because F is 1 over T, right? So that would be wavelength times frequency in Hertz, or a Hertz is the same as 1 over second. So again, you get length meters per second. So the units come out right. So propagation velocity is either lambda over T over a period, wavelength over period, or wavelength times frequency. All right. So I think what I'll do is go back to a page here. Okay. All right. Find the velocity of a wave. So we're looking, let me get my pen back. We're looking for V. That's what we're looking for, the velocity of the wave with a wavelength. What's the symbol for wavelength? The lambda. The lambda is equal to 2.5 meters. That is one long wavelength, okay? With a frequency of 44 hertz. Frequency is F, and that's going to be 44 hertz. So what would be the velocity? What was that formula I just gave you? Is lambda times F, okay? And that would be 2.5 meters. And rather than call it hertz, I'm going to say 44 per seconds, okay? 1 over second, okay? So 2.5 times 44 would be 120. Is that right? I'm doing it in my head. Second? 110. Okay. 110. And that would be meters per second, which is a great unit for velocity. right? 110 meters per second. You had two significant digits there, two significant digits there, two significant digits there. That zero is not significant. 110 meters per second. And that's a, well, we'll leave it like that. Now, the next concept here is superposition of waves. Now, what do we mean by that? When two waves of a similar type, meaning both longitudinal, both transverse, but basically even more than that, through the same medium, a new wave is created by the superposition of waves. Okay? The new wave is the algebraic sum of the separate displacements. So this is going to be sort of hard to, they don't do a good job of defining it, so I'm not going to write all that down. But let's talk about, so I'll just write this down, superposition of waves. So two waves are adding together somehow. Now, they add together in a couple of ways. One way is constructive interference. And the other way is destructive interference. Okay. All right. Constructive interference, if one wave is increasing, the other wave is increasing at the same time, then they go up higher than either one of them. But if one wave's increasing at the same time, the other wave's decreasing, then they tend to cancel each other out. That's destructive interference. Okay? Now, sort of hard to so let's see if I can. This is two waves adding. More than either one. Okay, destructive is two waves subtracting to be less than either. Okay, now let's go back to the other slide. This is such a pain in the neck. I have to go through this every time. All right. All right. Here's the example of that. Oh, my goodness. Okay. Here's a wave up here. There's a wavelength. Okay, this wave happens to be increasing here. When it reaches here, it starts decreasing, reaches equilibrium position again, keeps decreasing till it reaches its trough, increases again, it goes through this. Here's a second wave, increasing here till it reaches its max, then decreases here, equilibrium, back to its trough, equilibrium, up again. So let's look at what happens if you add these two together. Okay, we've drawn this one and this one on the same graph here. Here, this one is adding to that one, so the result is greater than either one of those, right? Mm-hmm. Until sometime, somewhere in here, this reaches a max. But now this wave is decreasing. At the same time, that's increasing, but this one decreasing more rapidly, that's increasing slowly. So this, the composite wave, the superposition wave, starts decreasing, okay? It goes down Down here, this has reached the minimum. This is still positive here. This is negative, but it's more negative. So it's dragged the superposition down to be quite, fairly negative. but it's still the sum of these two. It just happens to be at this point here, this one is this high above, that is the same distance below, that puts us the superimposed wave right at equilibrium position. It's at a 0 there. This one's a positive, but the same value, that's negative, that adds to 0. Now they both, this one outweighs this one and pulls it down. Then, certainly where they do cross at the same time, that sum's going to be 0. But this one's decreasing, this one's increasing, this one pulls it up a little ways, but not so much because this one's still decreasing, back to equilibrium where the amount above here is equal to the amount below there. And then you reach your absolute minimum here, where both of these are negative, and they add to be even more negative. So you have, this is a superimposed wave, superposition of two waves. You could have more than two, and these can really get weird. Okay. Now, if this were music, and music is waves, right? Okay. If you have something that's doing like this, you're going to have a strong beat here, a softer beat here and here, but you still have a beat, and then a strong beat here, strong beat here. So you'd have a something like that because of what's happening here. This is your addition of the two waves, superimposed waves, a strong beat here and here, weaker beats in between, strong negative beat here. This was preceded by a negative beat. So you have strong, weak, and that gives you sort of what they call a beat frequency. Okay. Now, this is a sort of a trick question. How would you measure the wavelength of this superimposed wave? From this crest to that crest, not to that one. It would be this one to that one, okay? So this, the wavelength is longer than either one of those two wavelengths. Now, most of the time we don't worry ourselves with that, but that's what you do. Equal position, how long it took to get there. Here to there. Same tail. Here to whatever the next one would be. Okay. Second?
Okay.
Yeah. So that's not super important here. You're not going to be tested on that, but just that's what you would have. Now, the next concept here is that of a standing wave. And we don't have much more time, so let's get what we can done here. Let me go back to this and that and that. Okay. When a transverse pulse reaches, okay, yeah. I think I will go back. Okay. No, that's not what I want. Okay. Started to use this, but I decided not to, but now I'm deciding to again. Here's what we've got. I mentioned this before. This is a transverse wave. You've taken the hose, swung it up in the air and down once, created a single pulse, a disturbance. The disturbance moves down the thing, but when it hits a fixed endpoint here, surprisingly, it inverts, reflects, and comes back this way. So it goes down, hits there, the energy is transferred back this way, but now it's downward, and the wave comes back here. Okay, that is a reflected wave, and they say in the spring, that has the same amplitude as the incident wave. Like I said before, when you did the spring one time, you see that impulse go down, but then you see it bounce and come back. And you can measure that compression there as being the amplitude. Okay? So this is a single pulse, not a regular wave. Okay. So that is what's happening when you've got a reflection there. Now, what they're talking about next is what they mean by a standing wave. If you have a fixed endpoint here, okay, and you pluck this thing, you're fixed up here too. This is 1/2 of a wavelength, okay? The length of this, say, do any of you play, either of you play musical instrument? Neither? Do you? You do, what? A what?
Clarinet and piano.
Okay. Now, I don't know if you realize what's going on inside the piano. When you hit a chord there are tension, what do they call them?
This is piano wire.
Huh?
Just the wire.
Piano wire, and they're fixed at both ends. You're hitting that. Okay? Now, if it does one thing, an entire wavelength would be that, so this is exactly 1/2 of a wavelength. This is 1 wavelength here. This is 1.5 wavelengths here. See, it's going 1 to here and 1/2 or more. And then this is 2 wavelengths. Okay? All those would be different frequencies, but they would be harmonically similar to each other. And those would be sounds that would be good with each other. Like when I used to play the piano, a lot of my sounds weren't good with each other because they hit the wrong key, and it would sound really bad. Okay? So this is what we call standing waves. When you get something that repeats a pattern like this, but they have to be exactly 1/2 wavelengths off from each other. If you had one coming down that was here, that's not going to reflect back real well. But if you had them exactly 1/2 wavelengths apart, then these will form standing waves. I think I've asked this a few times before. I don't know, I haven't been to McLean Science Center lately, but they used to have this wave machine over there, and you could, it was a strobe light, and you could spray, what do you call it? Atomizer, like your perfume you put on, but spray water like that, and then do the, set up the signals, and you'll see these standing waves set up. Sometimes they'll be chaotic, other times they'll form, and it looks like there's a node right here. There really isn't. The things are moving constantly, but there is a node there, and those form what we call standing waves. So these are examples of those standing waves. Standing waves in a string generated by increasing the frequency of vibration. This is, if you call this 1, this would be 2, 3, and 4 would be the frequency. You get 4 half waves per unit time, or you get 1 half wave per unit time, so it would be 4 times the frequency. All right, I think we're just about out of time. Let's see, where's a good place to stop? Okay, the next thing is interference and diffraction, so that will be where we'll begin next time. Okay, I've got to find, oh, here's my papers. Okay, did we get far enough along for you to have any homework on this section? They didn't have any problems at the end. Even though we did do one example, they don't have any problems at the end. So we'll finish 16.1 next time in just a very short time. And then we'll get to electromagnetic waves in 16.2. That's a fairly short section, but it has several examples. Then we'll do sound waves that y'all will probably be more interested in. That's 16.3. And then we'll talk about some characteristics of sound waves like the Doppler effect. Okay? That has a few examples. We'll do a little bit with resonance, but not a whole lot. And we'll just touch on simple harmonic motion just a little bit, because all those have some fairly reasonable applications that you might use in your sonography. Okay. So, any questions? All right. I appreciate your hanging with us at the end.
Did you break the last test?
Yes, as long as it came in before tonight, yeah, I got it graded let me let you see what you did. Is this the right stack? Okay. I think. Tiara, right? Okay. Want to see yours? Okay, now you can't, yeah.
I wrote down multiple answers.
Oh, I see.
I messed up on rounding. Terry.
On what?
On rounding.
Well, yeah, but I didn't count off for if it was just rounding.
Okay.
Well, if it was far enough off that it wasn't quite the same number, I took off maybe 1 or 2 points.
Okay. Okay. Fair enough.
But if it was within, like we were seeing, we would get 1.73 in the book or get 1.71. That's
Something
close enough.
minuscule.
Yeah.
Okay. Okay. Thank you so much.
Good deal.
I was way off on the ones I was off on.
What's that?
I was way off on the ones I got wrong. I was way off.
Yeah.
Thank you.
Yeah. Now, I hope I read your units that didn't confuse any of that. At first, I thought this was 7.567 something. I thought, oh, no, that's foot pounds, because it looked.
My fiance always tell me to stop wearing bed heels.
Yeah, and I saw the little tick through it. And see, I always slash my 7, so I thought that was a 7. I thought, nope, that's an F. So my work study student had circled it, and I went, wait, no, that's right, because she thought that was a 7 too. But you see, that next one, I was looking if there had been another digit in there, but that was
No,
off by a factor of 10. So
Yeah, I got that. That's what I kept looking at. I got that one completely wrong.
yeah, okay.
Thank
But
you.
the other, like that's just a round off thing, so I put okay. You got full credit for that.
And I don't know what made me put watts right there instead of foot pounds, but
Which one?
that one. I put watts.
Oh yeah, well that's all right. If you got the number right, I figured you had the unit. You just wrote down the wrong one.
Thank you again.
All righty. Have a good week. We'll see you next time.